Okay. Okay, so our speaker today is Pavel Semukhin from the University of Oxford, speaking about the membership problem for the 2 times 2 integer matrices. Please, Pavel.
Okay, thank you, Katya, for inviting me to give this talk. So, as you can see from the title, I will talk about the membership problem for matrix semigroups. So I start with the main definition of the problem. Then I will give a brief historical overview. And then I will go through a proof of one of my recent results on this topic. Yeah. So the membership problem is stated like this. So as an input, we have a finite collection F of square matrices in some dimension and a target matrix M. And the question is, does M belong to the semigroup generated by F? In other words, can we express M as a product of some matrices from this set F? And of course, in this product, we can use the same matrix as many times as we want. Yeah. So this is the general statement of the membership problem. And it's been known for a long time that in general, this problem is undecidable. And even, well, for example, Markov showed in 1951 that this problem is undecidable for 6 by 6 integer matrices. And a few years later, Mikhailova showed that this problem is undecidable in SL4Z, which is the group of 4 by 4 integer matrices whose determinant is equal to 1. Later, it was improved by Patterson, who showed that the membership is undecidable for 3 by 3 integer matrices. But here we don't have such a restriction on the determinant. And in fact, it's an open question whether the membership problem is decidable for matrices in SL3Z, where SL3Z is 3 by 3 integer matrices with determinant 1. Okay, these were undecidability results. For decidable case, we have the following result, that the membership problem is decidable for matrices from GL to Z, where GL to Z is the group of 2 by 2 integer matrices with determinant plus or minus 1. And this is a relatively recent result from 2005. Also, it can be derived from previous results, which were known from from the 80s, but they were not stated like in this form. Also, it's known that the membership problem is decidable for commuting matrices. And in fact, this problem is decidable in polynomial time, and also it is decidable in any dimension for commuting matrices. But for the non-commuting matrices, we had only this result here for GL to Z. And so in our recent work, we extended this result for GL to Z into a larger class of matrices. Namely, we proved that the membership problem is decidable for all 2 by 2 integer matrices with non-zero determinant. And we also have another result which says that the membership problem is decidable for 2 by 2 integer matrices with determinant 0 or 1 and minus 1. So in other words, we extended a previous result for GL to Z in 2 kind of orthogonal ways. In the first case, we extended it to all matrices with non-zero determinant. And in the second case, we have all matrices with zero determinant and the matrices with determinant plus and minus 1. And this leaves an open question whether the membership problem is decidable for all 2 by 2 integer matrices with arbitrary determinant. And it might look like it would be possible to somehow combine these two results to get a proof for the general case. But unfortunately, that's not so easy. Right? And in fact, well, it looks like it's not really possible to combine these two theorems together to get the general result. And well, I personally think that some completely new ideas are required to solve this problem for all 2 by 2 integer matrices. And so in this talk, I will go through main steps of the proof of this first theorem here for matrices with non-zero determinant. And I will use the notion of, I will be using the word non-singular, which simply means matrices with non-zero determinant. And so this is the theorem I would like to prove, which is stated as follows. So, we are given a finite collection F of 2 by 2 non-singular integer matrices, and also a non-singular target matrix M. Then it is decidable whether M belongs to the semigroup generated by F. Okay. Now, the first step to prove this result is to split this set of generators F into two subsets, which the first consists of matrices, let's call them M1 to Mk, whose determinant is not equal to plus or minus 1. And the second set consists of the matrices, let's call them N1 to Nr, such that their determinant is equal to plus or minus 1. In other words, they belong to GL to Z. And now let us consider a semigroup as generated by these matrices here from GL to Z. Then we have the following equivalence. That a matrix, the target matrix M, belongs to the semigroup generated by F if and only if there exists a sequence of indices, let's call them I1 to IT, and the matrices A1, AT, AT plus 1 from this semigroup S here, such that M can be expressed as the following product. So we have M equals A1 times MA1, A2 times MA2, and so on. And why this is the case? Well, it's easy to see, because if M belongs to this semigroup, then it means it can be expressed as a product of matrices from F. Yeah. And in this product, we can pick up matrices from the first set, which are shown here in the blue color. And the matrices from GL to Z, we can group them together and denote them by matrix by A1, A2, and so on. And by definition, this will be the matrices from this semigroup S here. Right? Well, this is quite straightforward observation, but it's important for the proof. Yeah. And the most important thing here is that the value of T here in this equation is in fact bounded. And it is bounded because the matrices, this blue M matrices, they have determinant whose absolute value is at least 2. Right? And it means that the value of t must be less than or equal than a binary logarithm of the absolute value of the determinant of the target matrix M. And now, once we have this observation, we can solve the membership problem as follows. So to decide whether M belongs to the semigroup generated by F, we can just go through all possible sequences I1 to IT of length up to this logarithm of determinant of M. And for each such sequence, check whether there are matrices A1 up to AT plus 1 from S, from the semigroup S, for which this equation holds. And if for one of these sequences, we have that there are such matrices from S which satisfy this equation, then we output that the matrix M belongs to the semigroup. Yeah, and in the other, in the opposite case, the answer would be no, of course. Okay, so now we need somehow to decide for a given sequence of such matrices M1, MI1 to MIT, whether there exist matrices from the semigroup S that satisfy this equation. And this is what we are going to prove next. Yeah. And I explicitly stated this theorem so that we know what we are proving. So what we want to show is that for a given non-singular matrices M and M1 to MT, and for a given finitely generated semigroup S from GL to Z, it is decidable whether there are matrices A1 to AT plus 1 from S such that this equation holds. Yeah. So if we can show this result, then it will imply that the membership problem is decidable. Okay, and the proof of this theorem goes by induction on this T. And in this talk, I will consider only the case when T is equal to 1, because it is this is the most important case. Okay. And then the rest of the proof just goes by induction. So for T equals 1, we have this simple equation. M equals A1 times some M1 times A2. And to solve our problem for this type of equation, we will use one result from algebra. It's called Smith's normal form theorem. And for the 2x2 matrices, it looks as follows. It states that for any matrix A, which is 2x2 integer matrices, there are matrices E and F from GL to Z, meaning that E and F have determinant plus or minus 1, such that matrix A can be written as E times the diagonal matrix M0, 0, some n times M times the matrix F, where n and m are some natural numbers. And moreover, these numbers n and m are uniquely defined by the matrix A. And this diagonal matrix in the middle, let's call it D, it's called the Smith normal form of A. So the Smith normal form of A is uniquely defined by this matrix A, but the matrices E and F are not unique here. And in fact, for any A, there are always infinitely many such E and F which satisfy this equation here. But this middle part, middle diagonal matrix is unique. Okay, now from this theorem, it follows that if we have the equation M equals A1, M1, A2, where A1 and A2 are from GL to Z, then it necessarily means that these matrices M and M1 must have the same Smith normal form. And let's call this Smith normal form D. And if they have different Smith normal form, then such equation does not have a solution for where A1 and A2 belong to GL to Z. So because of this, we can now reduce our case, this equation, to a simple equation where we have just the matrix D instead of M and M1. So using previous theorem, we can kind of transform this equation into a simpler equation, D equals A1, D A2, where D is the diagonal matrix 1n. And now the question we want to solve is the following. So we are given a matrix D, and we are given a semigroup S, and we want to know whether there are matrices A1 and A2 from this semigroup which satisfy this equation here. Basically, we want to show this theorem that for a given D of this shape and for any finitely generated semigroup S from GL to Z, it is decidable whether there are matrices A1, A2 from S which satisfy this equation. If we can prove this theorem, then we prove the base case for our main theorem. And so, in fact, the rest of my talk will be devoted to the proof of this result here. Okay, let's proceed with the proof. First of all, note that we can rewrite this equation here simply as A2 inverse equals D inverse times A1 times D, where, well, this is just the same equation as above. And this matrix here is equal to A1 conjugated with the matrix D. Now, let's look a bit closer to this on this equation. So let A1 has coefficients like A1, A2, A3, and A4, and A2 has coefficients B1, B2, B3, B4. Then if we substitute these matrices into this equation here, then A2 inverse will be this matrix here, and A1 conjugated with D will be this matrix here. And note that we have, like in this bottom left corner, we have a kind of entry which looks like A3 divided by n. Right? But here on the left-hand side, we have minus B3, which is an integer number. Right? So it means that if this equation holds, then this A3 divided by n must be an integer number. Right? And so let us consider a group, a set of matrices, let's call them H, which consists of matrices from GL to Z, for which n divides this entry A3 here. So by definition, we have that a matrix A belongs to this set H if and only if A conjugated with D has integer coefficients, or in other words, it belongs to GL to Z. So note that A conjugated with D always has determinant plus or minus 1 if A has determinant plus or minus 1. And so the fact that it belongs to GL to Z simply is another way of saying that it has integer coefficient in this case. And it turns out that H, the set H here, is a subgroup of GL to Z. And moreover, it is a subgroup of finite index. And its index is at most n squared, where n is the same as n here. And this will be one of the important ingredients in the proof. Okay, now we need some facts about the group GL to Z. Well, it's known that this group is generated by three matrices, which I will call S, R, and N. And S is this matrix 0, -1, 1, 0. R is the matrix 0, -1, 1, 1, and N is the diagonal matrix 1 and -1. And so any matrix M from GL to Z can be written as a product of these matrices. In other words, it can be represented by a word over this alphabet sigma, which consists of letters S, R, and N. However, such presentation is not unique because it's easy to see that S squared is equal to R cubed is equal to minus identity matrix. And because of this relation, such presentation is not unique. However, for every matrix M from GL to Z, there exists a unique canonical word W, which represents N. And by canonical, I mean the following, that the word W is canonical if it does not contain subwords like SS or RRR, and the matrix N appears only in the first position of W, or it doesn't appear at all. Yeah. And it is a very well-known property of the group GL to Z that for every matrix M, there exists unique canonical word which represents this matrix. Yeah. And this property will be used in our proof. Okay, next we need a notion of a regular subset of GL to Z. Now, we say that a set S of GL to Z is regular if there exists a regular language L over the alphabet S, N, and R, which has the following two properties. First, every word W from L represents a matrix from the set S. And the second property is that for every matrix A from S, there is at least one word W from the set L, which represents A. It may be easier to understand this definition by the following example. For example, a semigroup is an example of a regular subset. Because if we have a semigroup S, which is generated by matrices M1 to Mk, then we can take words W1, Wk, which represent these matrices, and then consider a regular language which is defined by this expression, by this regular expression W1 plus Wk star, or equivalently by this automaton here. So this automaton has one initial and one final state in the middle here. And then for every W, we have a path from this state back to itself with label W. And then it's easy to see that this language describes this semigroup S in this sense, as I stated above. And obviously, this language is regular. And so every semigroup is a regular subset of GL2Z. And for our proof, we will also need the following theorem, which states that the group H, which we defined previously, which consists of the matrices from GL2Z, where n divides this entry here, A3. So this group is also a regular set. And in fact, we can prove an even stronger result, that if we take the set L of all words W, which represent some matrix from this group H, then this set L is a regular set. Note that this is a stronger property than just being a regular set, because in the definition of a regular set, it's enough to choose a regular language L such that for every S, there exists at least one W, which represents A and that belongs to this set L. But for this group, we can take all possible words W, which represent all matrices from this group, and still this set L will be regular, which is, by the way, not the case in the general setting. For example, in the previous example of the semigroup, if we take all words W which represent matrices from the semigroup, then such a set will not be a regular set. It only will be a context-free set. But for this special group H, we have a stronger property. And in the literature, you sometimes find that such sets are called recognizable sets. And the proof of this theorem is actually quite simple. And it goes as follows. So let us choose representatives of the right cosets of this group H in GL2Z. And let's call them U0, U1 up to some US, where U0 is equal, we can choose it to be equal to the identity matrix. Then the automaton A, which recognizes this set L, has the states which are these representatives of the right cosets of H. And U0 is both the initial and the final state of A. And the other states are non-final, of course. And the transitions are defined by this simple rule. So we have a transition from UI to UJ with label R, if and only if this product UI times R times UJ inverse belongs to H. And we have the same rules for S and for N transitions. Let's consider one example. So let's take D to be this diagonal matrix with 1 and 2 on the diagonal. Then in this case, well, first of all, the group H consists of the matrices for which this entry here, A3 is even, right? Because N is equal to 2 in our case. And it's not hard to see that this H has index 3 in GL2Z. And here are this U0, U1, and U2 are the representatives of the right cosets of H in GL2Z. So our automaton for H will have 3 states, which are labeled by U0, U1, U2. where U0 is the only initial and the only final state in this automaton, and the transitions are pictured here. For instance, let's consider these two states, U0 and U1. Yeah. We can compute that U0 times R times U1 inverse is equal to this matrix here, where this entry, bottom left entry, is even, so it belongs to H. It means that by definition, we have a transition from U0 to U1 with label R. And you can check in a similar way that all other transitions look like this, like in this picture. Okay, now let's go back to the proof of the main result. So as we noted, every semigroup S is a regular set, and so let M be an automaton that recognizes such semigroup. And for this M, we want to construct two new automata. The first one will be called inverse of M, which recognizes the inverses of the matrices from the semigroup S. And the other will be called F of M, and this automaton will recognize the following subset of GL to Z. Basically, we want to recognize all conjugates BD of matrices B from S. The problem here, however, is that these matrices B conjugated with D might have fractional coefficients, right? And we want to work only inside the group GL to Z. So instead of taking all matrices B from S and conjugated it with D, we also add this additional constraint that B should belong to the group H, where I remind you that by definition, H consists of the matrices from GL to Z for which this conjugate has integer coefficients. So if we add this extra condition, we will have that B conjugated with D will be an element of GL to Z. Right? So this set, which I called S conjugated with D, is a subset of GL to Z. And the main step in the proof is to show that this set is a regular set. Yeah. And we prove it by constructing an automaton, which will be called F of M, which recognizes this set here. And if we have these two automata, like inverse of M and F of M, then we can decide whether this equation here, A2 inverse equals A1 conjugated with D, which is, by the way, the same as this equation D equals A1 D times A2. So we can decide whether this equation has a solution A1, A2 from S, if and only if this intersection of these two automata for the inverse of M and for the F of M is non-empty. And recall that inverse of M recognizes the inverses from S, so it corresponds to this, to the left-hand side of this equation. And this automaton F of M recognizes the conjugates from S. So this F of M corresponds to this, to the right-hand side of this equation. And so if this intersection is non-empty, it means that there are matrices A1 and A2 from S which satisfy this equation. And conversely, if there are such A1 and A2, then this intersection here will be non-empty. And because these are regular languages, we can, of course, decide the emptiness for the intersection of two regular languages. There is one technical problem, however, is that, as I mentioned, for every matrix, there are infinitely many words which represent this matrix. And by our definition of a regular language, the automaton must accept at least one of these words for a given matrix from the set which it recognizes. And so it could happen, because of this non-uniqueness, it could happen that these two sets have non-empty intersection, but the languages of these two automata might have empty intersection. Yeah, and so to find a way around this problem, we need to insert here an additional construction of what we call a canonical automaton, in the following sense that for every automaton M, this can of M is the automaton which recognizes the same subset of GL to Z as M, but it accepts only canonical words. And so if we add this additional construction of this canonical automaton in this formula, then we obtain what we need. And then there will be no problem with this non-uniqueness, because for every M there exists only one canonical word. So sorry, for every matrix there exists only one canonical word which describes this matrix. And the construction of this automaton, well, it's not something that we did, it was already known before. And I'm not going into details, but roughly speaking, it works like this. So we take, to construct this can of M, we take the automaton M and we add new transitions to it in the following way. Like if we have a path from one state to another in M, which is labeled by, say, RRR, then we add a transition from one state to another with label minus identity, because R cube is equal to minus identity. And so if we add such a transition here, then we don't change the automaton, we change the language described by this automaton, but we don't change the set of matrices which is described by this automaton. And similarly, if we have a path with label SS, we also add a transition with labeled by minus identity. And if we have a path which is labeled by minus identity times minus identity, then we add an epsilon transition here, because minus identity times minus identity will be, of course, identity matrix, and it is represented by this epsilon, by the empty word. And so we apply this procedure to the automaton M until we cannot add any more new transitions. And this essentially will give us this automaton can of M. And of course, optionally, we can remove all non-canonical words from the language, because the set of canonical words is a regular language. Okay, now we need to construct these two automata for the inverse of M and for these conjugates as conjugated with D. And the construction of the inverse automaton is quite straightforward, so I will not talk about it. And I only talk about the construction of this of this automaton f of M for the set for the set of conjugates from the semigroup S. And well, let's think how we could construct such an automaton. So I just remind you that we are given a semigroup S, which is described by an automaton M, and we want to construct another automaton which recognizes all conjugates from this semigroup S with the matrix D. And we can use the following property of conjugates. It is which is like this. If we have a matrix A, which, for example, equals to SRS, then A conjugated with D will be equal to S conjugated with D times R conjugated with D times S conjugated with D. Right? And so if we can replace every transition in the automaton M, so for example, if we have a transition with label R in M, and if we can replace it with a transition whose label is R conjugated with D, yeah, then this would give us, and we do the same with all other labels, right? Then it will give us the automaton f of M. Right? So it looks like to construct this automaton f of M, we just need to compute conjugates of all labels of all transitions in the automaton M, and this will give us what we want. However, there is a big problem with this approach, because these matrices S conjugated with D and R conjugated with D, they have fractional coefficients. For example, if D has this shape here, then SD will look like this, and RD will look like this. And as you can see, we have 1 over n here in the corner. So these matrices have fractional coefficients, and therefore they don't belong to GL to Z. Right? And so we cannot use them in the automaton, because our automaton f of M must be an automaton which describes a subset of GL to Z. So all matrices should have integer coefficients. And to get around this problem, we came up with a new idea. And I will try to describe it. So recall that we want to construct an automaton f of M, which recognizes this set here, but we are only interested in the matrices which have integer coefficients. Therefore, we don't take all matrices B from the semigroup S, but we kind of intersect it with this group H here, which selects only matrices for which B conjugated with D have integer coefficients. And suppose that we have, well, recall that the set semigroup S is recognized by the automaton M, and let A be an automaton which recognizes the group H here. Then recall that the states of this automaton A for the semigroup H consists of the representatives of the right cosets of H in GL to Z. And suppose that the automaton M for the semigroup S has the states Q0 to QR. And first, we want to construct an automaton for this intersection here between S and H. And for that, we use the usual construction. So we take the Cartesian product between these two automata, M and A, and define the final states in such a way that it recognizes this intersection of these two sets. And then, after we have this, we need to replace all transitions in this product automata with new paths. And we do it as follows. So recall that originally we wanted to replace this R here a transition with label R with something which looked like R conjugated with D, but the problem was that R conjugated with D was a fractional matrix. So here we do something slightly different. So let's take some transition from this automaton with label R, and suppose it connects two states. One of them is Qi uj, and the second state is Ql um. And now let's take this, consider this product, uj times R times um inverse, where uj and um are these matrices here. Then, by the definition of the automaton A, this product here must belong to this group H. Yeah. This is how we constructed this automaton A. And because this matrix belongs to H, its conjugate with D, by definition of H, it must be an integer matrix from GL to Z. And so we can find a word W which represents this matrix here. And then we replace this transition here with a new path from this state to this state, whose label is equal to this word W. Okay, so now this is how our construction looks like. And note that this construction here doesn't really depend on this Qi and Ql, right? Because when we do this replacement, we only use these matrices uj and um. So in a sense, this construction is applied only to the automaton A, right? And then it's kind of simply extended to the whole automaton using this Cartesian product construction. So I want to give one example how this procedure works, but to make things easier, I will only consider the automaton A instead of this product M times A. And it looks like this. So suppose we have, let's take D to be this matrix 1, 2, and H in this case, H will be a subgroup of GL to Z, such that this entry here is even. And previously we constructed an automaton A, which recognizes this semigroup here. And this automaton looked like this. And so how this new replacement rules will look on this automaton. So let's take this transition here from U0 to U1 with label R. So first of all, we need to compute the matrix U0 times R times U1 inverse. It will be this matrix here, 1 minus 1, 0, 1. And then we need to conjugate it with D. It gives us this matrix here. And then we need to find the word W, which represents this matrix. And in this case, it will be word like RRS, RRS. And so we replace this transition with a path whose label is this word. So on the picture, it looks like an edge, but it's in fact a path whose label is written here. Next, let us consider, for example, this transition here from U1 to U2, also with label R. In this case, we need to compute U1 times R times U2 inverse, which happen to be the identity matrix. So when we conjugate it with D, we still get the identity matrix. And identity matrix is represented by the empty word. So we just replace this transition by an epsilon transition. And so this how these replacement rules look like. And note that I just want to recall that, okay, so this was the original automaton, yes, and I see, remember that kind of ideally we would like to replace this R, these labels R with R conjugated with D, right? To obtain the automaton which recognizes the conjugates of elements from H in this case. But we cannot do it because R conjugated with D is a fractional matrix. So we had to do this more complicated construction. So we take this R and we multiply it by this U0 and U1 inverse on the left and on the right hand side to obtain a matrix, to obtain such a matrix that we can conjugate with D and still have a fraction, an integer matrix. And in fact, notice that these matrices, which we multiply R on the left and on the right, they are different in these two different cases. Yeah. You see, we have this transition is labeled with R, and this transition also have label R. But because they connect different states in this automaton, in our algorithm, we multiply this R by different matrices in every time. And so in each of these cases, these two transitions are replaced by different paths with different labels. Like in the first case here, we replace it with this path, and the second R transition become replaced just with an epsilon transition. So it kind of makes the whole procedure much more complicated than the original simple approach. But the original simple approach did not work because we ended up with fractional matrices. But this more complicated procedure works, and we always have only integer matrices. We never go outside of GL2Z. Of course, now it requires a special proof why all this works, right? But it's mainly a technical work, and I will not go into details. I just wanted to give a high-level overview of these algorithms. And just to recap the most important steps in the proof. So recall that we only proven the base case when we have only one matrix M1 here. And so we want to find out whether this equation has a solution A1, A2 from the semigroup S. And we used Smith's normal form theorem to reduce this equation to a simpler equation of this form, D equals A1, D A2, where D is a diagonal matrix like this 1n. Then we rewrite this equation in this form, and we note that for this equation to have a solution, the matrix A1 must belong to the group H, which consists of matrices from GL to Z, whose conjugate is also in GL to Z. And we observed that H is a subgroup of GL to Z of finite index, and there is an automaton which recognizes H. Then we also used the construction of the canonical automaton, and then we constructed an automaton f of n, which recognizes the conjugates from the semigroup S, which have integer coefficients. And then we used this equivalence that such equation has a solution in S if and only if the intersection of these two regular languages is not empty. And this is how we can prove the base case of this theorem, and the other cases are go by induction. And that's kind of, this is the end of my talk. Thank you.
Thank you, Pavel,
Okay.
for your nice talk.
Yeah, thanks.
Are there any questions?
If I can, may I ask you what's the idea of prove another statement for the case when determinant is 0 or plus minus 1? What's the main idea of proof?
Well, we also used the Smith normal forms there. The idea, I just want, can I go back to the beginning? By the way, when we have matrices with determinant 0, kind of this basically the first step in this proof fails, because we don't have any bound on T in this equation anymore. Yeah, because the matrix M might have 0 determinant, and everything breaks down here. But when we have matrices with 0 determinant, their Smith normal form look much simpler. Let me go. Basically, Smith normal form for singular matrices look like this, where n is equal to 0. So it looks like 1, 0, 0, 0. And so instead of in an equation like this, instead of these blue matrices here, we would have this matrix of the form 1, 0, 0, 0. And then you can do some computations to show that if you take a matrix and multiply it on the left and on the right by such matrices, it basically kills everything except for the top left corner in the matrix.
Okay. Yeah.
So basically, in this equation, we compute how these top left corners of the matrices get multiplied together.
Okay. Yes. Thank you. I get it.
Yeah.
Okay. Any more questions? Comments? No. Okay. So let's thank Pavel again.
Thank you.